at this stage, we are now in the middle of this course, separation processes. And I hope that you have learned about other separation technologies like mechanical separation, gas absorption, adsorption, leaching, and all those different types of separation processes are very much important, especially when you become a chemical engineer or when you finish your program in energy and environment. So in the later part of this course, we are going to discuss other separation techniques, and it will include evaporation, humidification. It will include a very important process which is called distillation. It's one of the most important unit operation in the chemical process industry. So it's very important that you keep an eye on how we can calculate the number of transfer units in distillation, number of stages in distillation units. And finally, we will also discuss about drying processes as a separation technique. So we will do it like this. The same that I have mentioned earlier, that I will upload a video lecture on different separation techniques that we are going to learn in this course. And I will also recommend you some problems that you will try to do by yourself, and I will also upload their solution in the canvas. So for this evaporation processes, I have uploaded a video lecture and also recommended problems. And I have also shared a short video on how you can solve one or two different problems in the evaporations, like single stage evaporators, which is also called single effect evaporators, and also multi effect evaporators. And I hope that you have seen those lectures. And so before you come to this Zoom meetings, it is very important that you listen and watch those videos. So during, like while you're watching those videos, it's important that you write down your questions, you write down anything that you feel that certain clarification is needed. And within these Zoom meetings, we are going to discuss your questions. So there is one way that you can write your questions in the chat section, so that I will look at the chat section. I will try to answer your questions one by one. The second thing, it is still possible while I'm going through the topic, you can just stop me and ask your question right away. And then I will try to answer your questions. It is very important in this course that if you ever find any problem, any query, please ask questions so that you do not have any doubts. Right? So it's very important that we learn about all these separation techniques which are you going to use in your practical life. So today I'm going to start my part in the course from evaporation technique. And I would like to suggest you that if you have any questions, please write down in the chat section, or if I'm going through the slides, you can ask your questions and stop me. So evaporation is a very important technique in many different types of chemical process industries. Like if you look at this picture, this is a picture taken from a Walmart company, which is a design company who design equipments for pulp and paper industries. And they also design multi-effect evaporators. So whenever we say multi-effect, it means the two or more evaporators are connected with each other in series or in parallel or in different forms. So these are type of big evaporators. They are used in pulp and paper industry. So in the pulp and paper industry, when we separate cellulose and hemicellulose from the lignin, which is like a glue of the tree. So when we separate lignin, it contains a lot of energy value. And since we use a lot of water, a lot of inorganic chemicals in order to separate cellulose and hemicellulose from the lignin, we need to evaporate the water. Normally, when we get that material, it is called black liquor, and black liquor has a water content of around 80%. So 80% of water and 20% of lignin and the inorganic chemicals. So in those 20%, half is the organic material, which is lignin, and half is the inorganic chemicals like sodium hydroxide based different types of chemicals. So it is very important for pulp and paper companies that they use the energy content of the lignin. So what they do, they use multi-effect evaporators, and they try to concentrate they try to concentrate the black liquor in a way that 20% dry solids should be increased to around 60, 70, or sometimes 80% of dry solids. And then it become a very thick liquor, and then it is a possibility to use it as a fuel in boilers. So they burn the lignin and they produce heat and electricity in the pulp and paper industry. So apart from pulp and paper industry, there are many different types of industries which also use evaporators. Like food industry, they use evaporators. Like milk industry, they use evaporators in order to produce concentrated milk or condensed milk. And pharmaceutical pharmaceutical companies, they also use evaporators in order to achieve a certain purity of different types of medicines. Fertilizer industry, they use a lot of evaporation units. And when they produce urea, which is one of the most important fertilizer, so they produce urea and it is in a slurry form. It contains a lot of water. So normally it is like 30 or 35% of the dry solid content and around 60 to 65% of the water. So they have to increase the concentration of the urea, and they have to evaporate water. And a lot of energy is consumed in evaporators. So as a chemical engineer or as a process engineer, it is very important that we design our evaporators in a way that it should consume less and less amount of energy as compared to other different processes. And evaporation is a very energy intensive technique in order to separate water or different types of liquids. If I can give you an example, in the pulp and paper industry, evaporators, only evaporators, they consumed around like 35% of the total energy demand of the pulp mill. So they are pretty huge. So they use a lot of energy. So in this discussion, I'm going to give you a very brief overview about the evaporation, different types of evaporators, and how we can measure the energy balances or material balances around the evaporators, right? So the main learning outcomes will be that I will discuss very briefly about evaporation, what are the industrial applications of evaporation process. I will discuss very briefly about single effect and multi effect evaporators, and I will give you a very short introduction about how you can perform the material and energy balances. There is a one chart that I'm going to show you, which is called enthalpy concentration diagram, which is also very important, which gives us information about how the concentration of any solute in a solvent or in a solution, how it affects the energy content of the solution. So if we know the concentration of a particular solute in the solution, we can calculate the enthalpy, which is the overall energy content of the solution. So we start from what is evaporation. We normally see that evaporation is a technique where you just vaporize the liquid. Sometimes you boil the liquid. Sometimes evaporation happens almost at every temperature. Like for example, if you wash your clothes and just put it outside, you are not boiling your clothes, but still the evaporation takes place in order to dry your clothes. So evaporation takes place at different temperatures, at very low temperatures as well. But when we talk about commercial evaporation, it means that we try to boil the liquid and try to vaporize the solvent as much as possible in order to increase the concentration of the solute in the solution. So this is called evaporation. If we look at the journal definition of evaporation, it can be relevant for any different types of solute and any different type of solvent. But in commercial processes, normally we refer it to the removal of water from aqueous solution, the solutions that contain a lot of water. And normally evaporation takes place without giving heat, like at low temperatures or ambient temperatures, But when we talk about commercial evaporation, heat is supplied in order to speed up the evaporation rate. There are number of factors that affects the evaporation, and these are some of the most important properties of the liquid or of the material, or some drawbacks during the evaporation processes. And one of the most important property is the concentration of liquid. So for example, if you have a very thick solution, so when we say thick solution, it means it contains a lot of solute in the solvent, so it is a very thick, so it is very hard to boil that like that solution. And normally the boiling point of the solution is a little bit higher than the boiling point of the pure liquid, and which is also called boiling point elevation, and I will discuss that boiling point elevation as well. So concentration of the liquid is very important in pharmaceutical companies or in the food industry. Temperature sensitivity of materials is very important. Sometimes we have to deal with certain types of solutions which are very much temperature sensitive. Like for example, if you are boiling your milk, and in order to produce condensed milk, it is you need to be very careful that how you give the heat, how you will provide the increase in temperature. So some of the materials are very much temperature sensitive. Some of the drugs or medicines that we produce in the pharmaceutical companies, they are very much temperature sensitive. So we have to evaporate the water or the liquid from those kind of material in a very delicate manner. Sometimes when we do evaporation, there has been formation at the top of the liquid. This is also a big challenge in the evaporators. We have to think about what kind of materials that are we going to use in order to build our evaporators. Sometimes we use like carbon steel in order to produce evaporators, or sometimes we use stainless steel. So it's very important what kind of material. We normally use those kind of materials in order to construct an evaporators which have high thermal conductivity, because if the material is not highly has like high thermal conductivity, you will lose a lot of heat. So high thermal conductivity is very important. And it is also very important that what should be the surface of the evaporator looks like. Will it have like very rough surface, or if it will be a very fine smooth surface? Because if you have a smooth surface within the evaporator, there is a very little formation of the scale, and the maintenance cost is a little bit lower. But if you have a surface which is a little bit rough, so there will be more opportunity of scale formation, so it will reduce the heat transfer coefficients. So we have to use all our knowledge from the heat and mass transfer in order to avoid the disadvantages, and also think about how we can improve the evaporation rates in the evaporators. So these are some of the most important affecting factors that affect the process of evaporation. How the evaporation equipments are classified. So there are different ways that how we can distinguish between different types of evaporators. One type is that we classify the evaporators in terms of their configuration of heat transfer surfaces, and sometimes they are also classified in terms of agitation or circulation system of the liquid. And there are many different types of evaporators: open pan evaporators, horizontal tube evaporators, vertical tube evaporators, long tube vertical evaporators, and forced circulation evaporators. So all these different types of evaporation equipment, they have their own advantages, they have their own disadvantages. So as a process engineer or as a chemical engineer, it is very important that you know for which application I'm going to use open pan or a horizontal tube or a long tube or a forced circulation, right? And you have to think about that I will choose a certain type of evaporator which have a high energy efficiency. It should have a high heat transfer coefficient. If the material is viscous, is it better to use open pan or a horizontal tube or vertical tube type evaporator? So this is you have to come into your consideration whenever you are going to select a right type of evaporator. So start with open pan evaporators. These are very, very simple construction. You have a open pan and you fill with the solution, and then you just heat it up, and then you let it the water evaporate as a steam, and then you try to concentrate the solution, right? But one of the disadvantages that the amount of heat that is required to boil the water, you just waste it, because all the steam, all the vapors that you produce at the surface of the evaporator, they just become part of the atmosphere, and you lose it, and you do not recover the energy content of the vapors. You cannot recover the energy content of the steam, right? So you lose all the energy that you have provided. But in many different cases, they are very simple and low in capital cost. So if you do not require, if your focus is not more on energy efficiency and the focus is towards the low capital cost or high operational cost, then you can choose open pan evaporators, right? So these kind of evaporators are a little bit expensive in terms of operation, because their heat economy is rather very poor as compared to other type of evaporators. There is another type which is called horizontal tube evaporators. If you look at the picture, there are horizontal tubes inside the evaporators, and then normally you can provide steam as the heating medium, right? And you put out your feed. Normally, steam enters to the tube and condenses and leaves out as the condensate. Normally, you use baffles in order to reduce the entrainment within the evaporator. And entrainment is a process where the solute particles are also escaping with vapors. So it is very important that you try to avoid the entrainment process, so that your solute particles should not escape with the vapors. One of the disadvantage is that their liquid circulation is very poor, and they are not very much suitable for viscous liquid. So when we say viscous liquid, sometimes we talk about if the solute concentration is little bit more than 50%. So they are very much thick liquids. It's not suitable for many different types of viscous liquids. Similar to horizontal tube evaporators, we have vertical tube evaporators. The overall construction of the evaporator is very much similar, but the difference is that the tubes are not placed horizontally but as vertically, right? So in terms of the construction, we can see that there is natural circulation, which is caused by the boiling of the liquid and decrease in the density, because we know when the temperature increases, the volume increases, and also the density decreases. And due to this high fluid mechanics of the feed, so you will have higher heat transfer coefficients, right? So the energy efficiency is little bit higher in these types of vertical tube evaporators. There is an also another type which is called long tube evaporators. Sometimes we use falling film evaporators or rising film evaporators. And in these type of evaporators, they are quite huge, they are quite high, and we use tubes which are like sometimes 3 to 10 meters long vertical tubes, and they are arranged in order to provide high liquid velocity within the evaporators. And these are widely used in the food industry, like for example producing condensed milk, right? So this is also a very important type of evaporator. Another very important type of evaporator is the forced circulation evaporators. In this type of evaporators, we use uh, pumps in order to increase the velocity, in order to increase the pressure within the evaporators, right? So we pump our feed into the evaporator, we use steam, and then steam transfers the heat to the solution and condense out. And normally in these kind of evaporators, heat transfer coefficient is little bit higher than other types of evaporators. And for example, if you are using a high viscous liquids, they can handle because of the pump, because pump they can push it with high velocity and with high pressure inside the evaporators. So if you really need to deal with high viscous liquids, the like some sort of forced circulation is also helpful in the evaporators. right? So these are some of the types of some of the types in evaporation equipments. So I would like to ask you that if you have any questions around the different types of evaporators and their working mechanisms, or otherwise I will proceed. So I'm wondering if you have any questions. Right, then I move on. And now I'll come to another important aspect, which is called the boiling point elevation. This is very important in case of systems or solutions where we are handling from very low concentration of the solution to a very high concentration of the solutions. And the boiling point increases, right? So this is a picture for sodium hydroxide. And if we know the boiling temperature of water, because you know that the boiling temperature of water is not same at different pressures. We know the boiling point of water is 100 degrees C when it is atmospheric pressure. So if we increase the pressure, the boiling point of the water will increase. If we develop a vacuum, like in order to reduce the pressure less than 1 atmospheric, the boiling point of the water will be lower than 100 degrees C, right? And it is, you can reflect it in terms of Kelvin, or you can also reflect in terms of Fahrenheit, right? So this picture is only for sodium hydroxide. If you know the boiling temperature of water at a certain pressure, you can calculate the boiling temperature of the sodium hydroxide solution when you know the mass fraction of the sodium hydroxide in the solution. So if you just take an example that we start from 200 degree Fahrenheit, so we assume that the boiling temperature of water at a certain pressure is 200 degree Fahrenheit, and we know the mass fraction of sodium hydroxides, let's suppose 0.70, right? So we start from 200 Fahrenheit, we go up till 0.70 mass fraction of sodium hydroxide. So it means the boiling point of the solution will not be 200 degree Fahrenheit, and it will be around, let's say it will be around like 340 or 345 degree Fahrenheit, right? So if you have higher concentration of the solute in the solution, the boiling point of the solution is much, much higher than the boiling temperature of the water. So if you look at the picture where you have the mass fraction of sodium hydroxide, let's suppose 0.10 or 0. So you can start from 200 and then you go there, so it is around like 0, and then the boiling temperature of the solution will be the same, right? So if the concentration is 0, if it is pure water, then there is no issue with the boiling point elevation. But whenever you increase the mass fraction or the concentration of the solute into the solution, it means the boiling point of the solution will keep on increasing, right? So it is very important whenever when you are solving problems related to evaporation, if it is not given that there is negligible boiling point elevation, right? So if it is negligible boiling point elevation, then you do not have to consider this picture. But if this information is not available in the problem statement, so it is important that you do not take the boiling point of water only. You have to consider the boiling point of the water versus the boiling point of the solution based on the mass fraction of sodium hydroxide, or any other different type of solute or a salt. But this picture is, we can use it only for sodium hydroxide as a solute. Now I will talk very briefly about the operation methods like single evaporators. In single effect evaporators, if you look at the overall construction, so you fill your material with the solution, and normally we feed a liquid which is called thin liquor. So thin liquor is a liquid which contains high content of water and low content of the solute. And normally we provide steam as the heating media in order to increase the temperature of the thin liquor. So after the evaporation takes place, the water or the liquid vaporizes and it is taken out in the vapor space. And the concentrated liquid is taken from the bottom and it is called concentrated liquor, right? And the steam, we use it at different pressures or different temperatures, and the steam condense out within the heat exchanger inside the evaporator, and when it gives out heat it becomes a condensate. So normally we have three functional sections within the evaporators. One is called heat exchanger, where steam is supplied and it transfers heat from steam to the thin liquor. The second part is called evaporating section, which is the main body of the evaporator. In this section, the liquid boils and the water or liquid evaporates. The third part is called the separator or the vapor space. So this is the part here. So vapors leaves the liquid phases and passes off to the condenser or any other equipment. So this is a very general construction of a single effect evaporator. I forgot to tell you about single effect evaporator, that whenever we talk about effects, effects is like one. So if it is a single effect evaporator, it means it has only one evaporator. When we talk about two effects, it means two evaporators are connected with each other or integrated with each other. When we talk about three effect evaporator, it means three evaporators are connected with each other. I will talk about multi-effect evaporators later, right? So this is the very general construction of a single effect evaporator. Normally we make an assumption that the boiling temperature within the liquid is equal to the temperature of the vapor. So whenever you need to calculate what will be the temperature of the vapors that are leaving the evaporator, then you can assume that the temperature of the boiling solution or boiling liquid will be the same as temperature of the vapors. And normally we can consider this assumption when we believe that there is a equilibrium between the vapors and the liquid. And normally we use single effect evaporators when we have a small capacity to handle and when we have a low costing, right? And normally the energy used as the latent heat of vaporization. This is a general construction of multi-effect evaporators. The reason of having multi-effect evaporator is that we try to increase the heat economy of the system. We try to increase the heat energy efficiency of the equipment. So we use evaporators are connected with each other. So what happens in the first evaporator, like if we take this example, so in the first evaporator, we add steam in order to increase the temperature within the evaporator, and the steam is taken out as a condensate after transferring the heat to the boiling liquid. And the vapors from the first evaporator, they are used as the heating medium for the second evaporators, and the vapors from the second effect are used as a heating medium in the third effect evaporator. So we only provide external heat in terms of steam, right? So only steam, we have provided only one evaporator, but the vapors that have evaporated from first effect, we use them as heating source in the second evaporator. So the vapors from the second effect, we use it as a heating medium source in the third evaporator, and so on, as many as we would like to include in the system, right? So overall energy efficiency of the system is much higher than the single effect evaporators, because you have only used steam once, but you have evaporated the water in two or three or more effects evaporator. And now the most important question that comes, that how we can perform a mass or enthalpy balance for single effect evaporators and similarly for multi-effect evaporators. So if we look at the construction for a single effect evaporators, right? So we have, this is the main body of the evaporator, and this is the vapor liquid separator, or so normally we can call it as a vapor space, right? So we provide heat. So let's assume that we say that ms is the mass of steam that is provided to the evaporator, and at a certain temperature it has an enthalpy hs. I believe that you know the concept of enthalpy from the thermodynamics. This is the energy content of a stream, and we normally can show it as enthalpy or energy content, right? So if we assume that the mass of steam is ms and hs is the enthalpy of the steam at certain temperature or certain pressure, and since the flow rate of the steam will be equal to the flow rate of condensate, because the flow rate, if there is no accumulation into the system, it means the flow rate in will be equal to the flow rate out. So the mass of steam will be equal to the mass of the condensate, but the energy content of the steam will be much higher than the energy content in the condensate. So it will be different. So you will have enthalpy of steam, which is Hs, and enthalpy of the condensate, because condensate will also be at a very high temperature, but the total enthalpy will be much lesser than the enthalpy of the steam, because that difference of enthalpy is the total amount of energy that is transferred from the steam to the boiling liquid inside the evaporators. So we have to perform one mass and energy balance on the steam side. Now we also have to perform the energy balance on the liquid side. So let's say if we have a thin liquor feed, it must have a certain flow rate. Let's say it is mf, and it is an enthalpy of hf, right? So within the evaporator, what will happen? The water vapors will evaporate and it will enter into the vapor space, and it is taken as vapor. And the rest of the material, which is thick liquor, it is taken from the bottom, and we can call it as thick liquor. Now, if we know that the mass flow rate of thin liquor, which is mf, and we call the mass flow rate of the thick liquor as m, so how much is the water evaporated? So the difference in the mass flow rate of the feed and the mass flow rate of the thick liquor, so this difference is the total amount of water that has been evaporated. So it will be mf minus m. Since the vapor is at very high temperature, so it means it will also contain a lot of enthalpy or energy content, and maybe we can call it as HV. And the thick liquor, because we have increased the temperature inside the evaporator, so it means the thick liquor will also be a high temperature, so it will also contain a certain amount of enthalpy or energy content. So this is like overall picture that what is going in: steam and condensate going out. The feed comes in, and then it is divided into two components: one is vapor and the other one is the thick liquor. Now we have to think about a certain assumption that condensed steam leaves at the same temperature of the steam, and the difference between the enthalpy of the steam and the condensate is the latent heat of condensation. So I hope that you have also know the concept of latent heat of condensation, latent heat of vaporization, right? So at this energy, the amount of energy that is transferred in terms of condensation, or the amount of energy that is transferred in terms of vaporization, right? So the difference in the enthalpy of the steam with enthalpy of the condensate is the latent heat of condensation, and we normally denote it as lambda s, right? So the difference, so this is the total amount of energy that has been transferred from the steam to the boiling liquids. Now we have to perform energy balance for steam side, and we have to perform energy balance for the liquid side. So the amount of energy that is transferred, or the rate of heat transfer through the heating surface from steam, it will be equal to the enthalpy difference, which is the latent heat of condensation, multiply with the flow rate of the steam, and we can denote it as m lambda s, right? And then we have to perform the enthalpy balance for the liquor side, right? So let's say we have to calculate how much energy is going out in terms of vapors. So this is the flow rate of the vapors, mf minus m. So this is the flow rate of vapors, multiply with the enthalpy of the vapors, minus this is the enthalpy of the feed. Sometimes if you have a feed at a temperature of, let's say, 25 degrees C, but at 25 degrees C there is a very little enthalpy is still there. So we have to consider any little part of energy that is carried out by the feed. So this is the flow rate of the feed, or enthalpy of the feed, plus this is the enthalpy of the thick liquor, right? So the total energy balance will be equal to how much energy going out from vapors, plus how much energy going out in terms of thick liquor, minus the total amount of energy that is uh, carried by the feed, and this will be equal to the total amount of energy that is supplied by the steam. So amount of heat transferred from the steam will be equal to the amount of heat energy within the liquid, right? So you can write in terms of, this is the transfer of heat from steam, and this total is the amount of heat within the boiling liquid. And this equation will only be valid. This equation will only be valid when there are no heat losses. And we assume that the evaporator is 100% insulated, so there is no heat loss. So the amount of energy transferred from the steam will be equal to the amount of energy within the boiling liquid, right? So this is how you can write the enthalpy balance for single evaporator. You don't need to memorize these equations, but it is very important that you understand that what information they are reflecting, right? So whenever you are solving your assignments, it is very important that what type of equation that you are going to use from the book. Normally, like in 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 um, in 2020 of this course. Now we have switched from the campus learning to the distance learning, and you do not have a final examination. But the same rule applies everywhere. If you are doing your open book examination at home or open book assignment, you don't need to memorize them, but it is very important that you recognize that for a certain problem, which equation I'm going to use, right? So this is the heat balance equation for single effect evaporators, but with an assumption that there are no heat losses. You can also write equations when you say that the heat of dilution within the system is negligible, right? So if the heat of dilution is negligible, then you do not use the pre, the previous equation, but you can use a new heat transfer rate equation that will be equal to the total amount of heat that are transferred to the thin liquor plus the heat of evaporation, which is the heat carried out by the vapors. And you can write your enthalpy balance like this: q is equal to, like, the same equation that you have used many times in heat transfer, mcp delta t. M is the mass flow rate, cp is the specific heat, delta t is the temperature differences, right? So you can write your enthalpy balance in terms of different types of heat transfer equations. This picture is an enthalpy concentration diagram, right? This picture or this chart helps us in finding if we know the mass fraction of sodium hydroxide, if we know the temperature of the saturated solution, we can calculate the enthalpy of the solution. So this equation is very important. Whenever you know the mass fraction of a solute in a solution, you know the temperature, you can calculate what could be the enthalpy or the energy content of the solution. So let's suppose we have a mass fraction of sodium hydroxide, let's suppose zero point 0.5, and we know the temperature of the saturated solution, let's suppose 250. So we start from zero point 0.5, we go till the temperature of the saturated solution, which is 200. Let's suppose this is the 200, and then we see on the y-axis. So it looks like that it will be around 215 or 220 BTU per pound of the solution. In the canvas, I have also added another enthalpy concentration diagram, which is in the SI units. So you will have a mass fraction, and you will have a temperature in degrees Celsius, and then you will have an enthalpy of the solution in terms of joules or kilojoule per kilogram of the solution. So it is up to you that what kind of enthalpy concentration diagram you would like to use, either in the British units or either in the SI units. I would like to ask you if you have any questions till now. Any questions? If you have any ambiguity, any doubt, please clear.
question about how you what you said before a bit. Does it matter if steam, the Q of the steam, and the unit of enthalpy of condensation? Yeah,
Yeah.
is the lambda S equal to lambda for vapor in the tables?
Yes, because whenever we call lambda for the steam, steam is nothing but vapors. Is this your question?
Yes, I consider it. Is it
Yeah.
just the same because yeah, the steam turns back into a
Liquid.
liquid. Yeah.
Yeah. Yeah. So okay. So now you have to consider two concepts. One concept is about latent heat of evaporation or latent heat of vaporization. So this is one thing. The other thing is latent heat of condensation, right? So latent heat of vaporization is the amount of heat that you provide to a liquid when it turns from liquid to the vapor phase or liquid to the gas phase, right? So whenever we boil the water at 100 degrees C at 1 atmospheric pressure, so you if you provide as much as heat possible at this temperature, at this pressure, the temperature of the boiling liquid will not change, but the liquid will convert into the gas phase. And this total amount of energy that you provide to the system is called latent heat of vaporization. Now, the opposite, when the vapors they just give out their energy, they become liquid, so they transfer back from the gas phase or the vapor phase back to the liquid phase, and the temperature is not changing, temperature will remain same, but they give out their energy, and that is called latent heat of condensation. So the main difference is that the phase is changing. In latent heat of vaporization, the phase is changing from liquid to the vapor. In latent heat of condensation, the phase is changing from vapor to the liquid. So it's an opposite, but the temperature will not change. So the lambda s will remain same for a certain temperature and pressure.
All right.
Yeah. Do we have any more questions? I could see there is something in the chat. Okay, so I will talk about the assignment later when I finish this short presentation about the evaporation. I will give you the detail. So, do we have any more questions till now? Then I will proceed. And since we have been talking about how we can perform energy balance in single effect evaporators, so now we have to think about how we can perform energy and material balances for multi effect evaporators, right? So normally it is quite similar, but the difference is that you only provide steam in the first evaporator, and then the vapors from each effect will become a heating medium for second effect, for the third effect, and so on. So in this type of configuration, we have steam at TS, which is used as a heating medium for the first effect, and it allows us that we boil the liquid at a temperature T1. So T1 is here and T1 inside here, and P1 is the pressure in the first effect. In the second effect, the vapors which are now as a steam, so the vapors from the first effect, they are taken as a heating medium for the second effect, right? So the ts2 it will be equal to the t1, so t1 will be the amount of heat, or sorry, the temperature of the steam, or the temperature of the vapors that are coming from the first effect, right? And the boiling point temperature of the liquid must be less than from the condensing steam or vapor in order to transfer the heat. So for example, the temperature of the steam must be higher than the temperature of the vapors in the first effect, and the temperature in the first effect must be higher than the temperature in the second effect, and the temperature from the second effect should be higher than the temperature in the third effect. So it means Ts should be higher than T1, T1 should be higher than T2, and it should be higher than T3. And this is quite similar for the pressures as well, right? So now how we can calculate the amount of heat transferred per hour. So if you remember that you might have learned a very important heat transfer equation for heat exchangers, and how we can calculate the rate of heat transfer. It is equal to UA delta T, and U is the overall heat transfer coefficient, A is the heat transfer area, and delta T is the temperature difference between the heating medium and the temperature of the solution or of the liquid. So if we take the energy balance for the first effect, so we call it Q1. So Q1 is the amount of energy transferred. It will be equal to the heat transfer coefficient of this heat exchanger. A1 will be the heat transfer area in evaporator number one. And what is delta T? So delta T is the temperature of the like boiling liquid with the temperature of the steam. So Ts minus T1, it will be equal to delta T1. So this is how you can calculate the amount of heat transferred per hour in the first evaporator. Similarly, you can perform for the second evaporator. The only difference will be if it is a different evaporator, then it will have a different heat transfer coefficient. If all the evaporators are same, they might have the same overall heat transfer coefficient. If the heat transfer area is similar or not, but you can call it like A2 for the second effect. And the most important thing to consider in the second effect, that what will be the delta T. So the delta T will be equal to the temperature of the vapors coming from the first evaporator with the temperature in the second effect. So T1 minus T2 will be the delta T2. And similarly, you can calculate for the third effect. Now we have to make certain assumption that if there is no boiling point elevation or there is no heat of the solution, sometimes there are some liquid when their concentration is increased, they result in a number of heat that is dissipated to the solution. So feed is supplied at boiling point. So if we have all these assumptions met, it means the total amount of heat transfer rate within the first evaporator will be equal to the heat transfer rate in the second evaporator and heat transfer rate in the third evaporator. And you can write your equations in terms of UA delta T for each evaporator, for first effect, for second effect, and for the third effect, right? So when you write your equations and if the evaporators are constructed in a way that the areas of all those evaporators are same, then you can write Q1 equal to Q2 or Q2 equal to Q3, and then you can write your equation. Then you will find an equation which gives us only the information about the relationship between the heat transfer coefficient and the delta T. And we can see that the temperature differences will be inversely proportional to the overall heat transfer coefficient in the two effects or multi effects, right? And if we arrange the same equation, we can calculate the delta T for first effect, delta T for the second effect, delta T for the third effect. The only difference will be this for the first effect, it will be 1 over U1, but for delta T2, it will be equal to 1 over U2, and for delta T3, it will be 1 over U3. And this will be the only case when the heat transfer coefficient is different in all these three different types of evaporators or heat exchangers, right? So then you can calculate delta T1, delta T2, and delta T3. And from this picture, you have to know that what is delta T1, delta T2, and delta T3. Delta T1, Ts minus T1, delta T2, T1 minus T2, and delta T3 will be equal to T2 minus T3. So you can calculate delta T and delta T1, T2, and T3 for as many effects that we are going to use in evaporators, right? So I have recommended you a couple of problems, and one problem is for single effect evaporators, and one problem for the multi-effect evaporators. And both of these problems are very much simple. And I have also uploaded their solution, like videos for their solution as well, in order to make you understand that how you can perform the calculation step by steps. Sometimes you have to use appendixes in the book which are related to steam tables, which are related to the properties of the saturated liquid or saturated steam. So you can calculate at what temperature and pressure you can calculate uh, the enthalpy or the volume or latent heat of vaporization or condensation. I will not go into their details, but maybe I can show you the appendices. Yeah, so this is appendix number 7, which is very important. It gives us information about properties of saturated steam and water. So if you know the temperature or if you know the pressure, you can relate them with each other. From this temperature and pressure, you can calculate the specific volume of the liquid or saturated vapor. Normally, in this chapter, we are not going to use them, but our focus will be on the enthalpy or the heat content. If you need to calculate the enthalpy of the solution, then you have to consider this enthalpy concentration diagram. But for the steam side, if you need to calculate at what temperature or pressure the latent heat of vaporization for the steam, then you can calculate it from this table. Or I will also upload many different types of steam tables as well that you can use in order to find the properties of the saturated steam and water, right? So for different temperature and pressure, you can calculate all different values. And maybe I can also show you. So this is, we have already discussed boiling point elevation diagram. We have discussed the enthalpy concentration diagrams. So I think we have already discussed those pictures that you are going to use in order to solve your problems. So I would like to ask you that if all of you have seen those videos regarding the problems, and if you have any questions, please ask at the moment. But I will do it like this. When we meet tomorrow to discuss humidification as the separation technique, I will devote first 5 or 10 minutes to answer your questions. So you still have an opportunity today that you will try to solve those problems by yourself and see that if you find any problem. Then when we start tomorrow, you can ask your questions about evaporation before I go into the details about the humidification part, right? So I would like to ask you if you have any questions now, we can discuss it. But if you also would like to discuss the problems in the evaporation section, then I will devote like 5 or 10 minutes before we start the humidification. So I'm wondering if you have any questions. And then maybe I can answer about the assignment for evaporation. I'll give you this week in order to solve the recommended problems for evaporation and for humidification. And then I will start giving you the assignments for evaporation and humidification. And I will add their deadlines as well in the canvas. So you will know that how much time it will take for all different assignments. It is very important that you try to send in um, uh, your solutions within the deadlines in order to get the good grades. If you submit your assignment after the deadline, and even if you have done your assignment correctly, some points will be deducted. So it is very important that all of you send in your assignments within the deadlines. Normally I will give you 5 days for each separation technology. So you will have 5 days in order to write the assignment for each separation technique, right? But it will be when you are done with the assignments that are given by Jurgen, right? And I will put those deadlines in the canvas as well. But first, within this week, it is important that you solve those recommended problems, and I have put their solutions and check that if you have done it right or wrong for evaporation and for humidification. Then I will start adding the assignments for them as well. So if you have any questions about the home assignments.
I have a question, Maza.
Yeah.
Is it necessary to, I don't know the English word, but interpolation, is
Yeah.
that necessary to do?
So sorry, I did not get your question.
Uh, I think that in some of the recommended problems for
Yeah.
today,
Yeah.
it was needed to, if you looked in the tables, the
Ah,
number
okay.
of
Okay.
decimal stats.
You mean to say like some interpolations?
Yeah, yeah. If
Ah, it's
one,
you don't. Okay, okay. I understand your question. Yes, yes. I was coming to that issue. Like normally, let's see. I can show you. So let's assume that now we have temperature 120 and 130 here, and maybe you have to work with a temperature which is 124 or 125. Do you need to do an interpolation or extrapolation? I think in these kind of problem, you don't need to do interpolation or extrapolations. You can just take an average and just take a middle number. So if you take a middle number, but you have done your steps correctly, then if a little bit change in your answer is different from others, it will be no problem.
okay, thank you.
Yeah, good. So you don't need to write very exact numbers. So this is what we normally give a flexibility. So if you do not have the exact number for, let's say, enthalpy or latent heat of vaporization, but it is in between, it is okay. It's not very hard and fast that you should have a very exact number. But how you do the steps, how you check the values, it is very important. So for example, the right number is, let's say, 1100 BTU per pound, but you have used maybe like 1095 or 1120. A little bit of the difference. It will not matter in your assignments. Right? So what we have. Okay, so do you want the assignment in English or Swedish? It is completely up to you that how you would like to write your assignment. If you wish, you can write your assignments in Swedish as well. So it's not a problem. I can read Swedish very well. So if you would like to write your problems or your assignments in English, perfectly fine. But if you would like to write your assignments in Swedish, perfectly fine. It is completely up to you how you would like to do it. Do we have any more questions? Right? But I still give you an opportunity, and we will do it like this in the future as well. That before I start the next topic, I will give you 5 or 10 minutes for asking your questions. If you find any questions and you would like to discuss, you can just send me an email. You can write me in the inbox within the canvas, whatever you feel like. It is very important that all your questions should be answered. So I will be very happy to answer your questions whenever you feel necessary. Right? So when you do your work, when you finish your recommended problem, whenever you find any issue, just write me an email and I will try to answer your questions, hopefully within couple of hours. So normally I answer my emails quite quickly. So don't feel worried. So whenever you find an issue, just send me an email and I will try to help you with it. So if you do not have any more questions, then I will see you tomorrow. I will again suggest you please listen and watch the video before you come to the meeting so that we can have a more productive and fruitful discussion. Right? So if you have any problem, you can just write or you can ask your questions right away. Right? So now I will say goodbye and then I will see you tomorrow. Right? And I wish you good luck.